Thanks. So, thanks for coming once again. This is lecture 4 of 5, and I want to remind that the last one will be about ADS3 CFT2 specifically. Most things I've said also apply in ADS3 CFT2, but if you have any questions about the higher dimensional story we're telling, today's the data app, and so I will try to put a bow on some of what we've been talking about by finally getting to some of the central results in the subject that really launched this reversal of the arrow moving from CFT into ADS, namely this Himster, Panadonis, Polchinski, Sully paper, which we've alluded to a bit. We'll talk a bit about that in detail. And then other constraints in the spirit of the bootstrap on the space of CFTs using some of the 4-point technology we prospect. And then I'll conclude with some open questions that I think are important for this field. And next time we'll almost start from scratch, introducing some techniques that are specific to CFT2 and the whole field. So, as some kind of bridge between last lecture and this one, before I start talking about this HPPS conjecture, I said that last time we talked a bit about some top-down bootstrapping of 4-point functions. So, for example, these works by Rostelli and Zhao and follow-ups, which derive these supergravity 4-point functions of half BPS operators and n equals 4 mils just by imposing some consistency conditions and then formulating an educated guess. So today's more about bottom-up, and I don't mean something like model building. It's more in the spirit of just imposing constraints and asking what models are even consistent, what models are even allowed. And so one thing that you can do is to, the bottom up strap. One thing you can do is to ask the following. So last time we talked about exchange amplitudes for 4-point functions, the pre-level exchanges in ADS. If you decompose them into conformal blocks, what operators do they include? If you do this in the direct channel, this includes some single trace operator O, or let's call it phi, sort of dual to the exchanged operator, plus a bunch of composites made of the externals. Right? So here. Now, can you reconstruct these kinds of exchange diagrams just from thinking about crossing at large n from the boundary? And the answer is yes. So, in other words, you can pose the following question. So, say you have your single trace operator O. You think about its OPE with itself. What appears? Well, there's the identity, and then there's the sum over these composites. Right. So this here was this generalized free field result. Right, so this would be the infinite central charge piece. And then at order 1 over root C, there would be some new single trace operator phi, and some other stuff, and then corrections to this. So you can ask, given the presence of this in this OPE, what does it imply about the rest of the spectrum? So how does it, for example, correct this piece? And that's the boundary version of asking this statement about the OPE data of exchange diagram. You say there's a single trace operator. If I have a 4-point function of O's, this will be exchanged, like so. So let's suppose there's some conformal block with the exchange of phi. Then what does this imply about the double trace composites corrected at order 1 over C? So what do you do? Well, you solve crossing. And you ask, what does the exchange here imply under crossing symmetry for the 4-point function expanded in the other channel? So what kinds of exchanges appear here? And so the answer is just the corrections to this composite OO double trace data that you would get if you computed a bulk exchange diagram. The answer, so this is the question. The answer is you get these pieces of data at 1 over C, which match the ones you get from an exchange diagram. So in this way, you can reconstruct the bulk exchange Witten diagram just by solving crossing at 1 over n, imposing the existence of a single trace exchange, and then asking how the rest of the data is affected by solving crossing. And what does solving crossing mean here? It means that there are certain singularities in the cross ratios that must be matched on both sides, and to match them, you must have a certain set of operators over here, with certain specific OPE data, in particular the anomalous dimensions and the OP coefficients of these things. So this is sort of a large C version of this light cone bootstrap story, which holds for arbitrary CFTs at arbitrary central charge. And whereas in arbitrary CFTs, the light cone bootstrap tells you there must be composites which exist at infinitely large spin. In a large C CFT, the small parameter is played by 1 over C instead of 1 over L, the spin. And so even for finite spins, like spin 0, you have these composites where their existence is a feature of large C, not because you went out to some asymptotic kinematic regime of large spin. So the moral here, which comes up again and again, even in ADS3 CFT2, there are versions of this where you constrain the partition function using modular invariance, which is a form of crossing, as we'll talk about next time. At large C, 1 over C sort of implies that things that are true in general CFTs are true over a wider range of validity for a larger range of kinematic parameters than they are otherwise. Okay. So that's sort of a lesson.
Can I say this lesson? Like, so if I want to add some sort of 1 over n, let me call that 1 over root C, 1 over n term with some coefficient, I can always solve the large n crossing equation in CFT by appropriately adding 1 over n corrections to the previous order 1 data.
Exactly.
And a solution always exists in the 1 over n expansion.
Yes, and that solution is a specific solution. So there are, for example, anomalous dimensions at order 1 over C, and then some corrections to the squared OPE coefficients, which we called A, which are specific functions of n and L, and have some dependence on the dimension of the single trace operator. And they're exactly the ones you would get from a bulk calculation, but yes, the statement is about exactly what you said about crossing.
So this 1 over n corrections, do they have to accompany some specific single trace operators, or I can add some?
Not yet, no. So this is the sentiment. This is kind of bottom up. We're saying if you have one, what is the contribution? And then later you can ask, well, how many of these do I have to have, or what do their quantum numbers have to be? So this is, if you like, at the level of specific individual diagrams, but the diagram itself follows from some Lagrangian. Then you can ask what bulk Lagrangians are okay, which is like higher level question. And the lesson I was trying to emphasize is that you can talk about spin 0 composites at large C, but at finite C, there's no well-defined notion of a spin 0 composite, because if you have some local operator O, then to bring two together to make another primary operator, something which is not in general well-defined, going to large spin, this becomes well-defined, which is what the light cone bootstrap taught us. And if you think in ADS terms, you can always make these bound states for arbitrary spins. 1 over C is doing that work for you. So there's this extended regime of parameters where things that are true at large spin, in this case, the existence of these operators themselves, is true all the way down to finite spin, as long as you have large C as a small parameter controlling your expansion.
Maybe I can ask my question. So I put etc. They're showing that the solution to crossing at large n were in one-to-one correspondence to the possible batch interaction. Is it that?
We're about to do exactly this.
Sorry. So you haven't that statement is not yet in what you wrote over there, because that's just
right. This is meant to be a kind of bridge to that, but this followed that. I mean, yeah, this is definitely chronologically after the HPPS story, which got us thinking in these terms. But it also connects into last time where we were talking about this. So it sets us up nicely to explain what you just said, which is what I'm about to do. Okay. Any other questions, though? All right. Let me actually take a new board for this. All right. So this paper came out in 2009, and just for some history here. So this Ratazzi, Richkov, Tony, and Vicky paper came out in 2008, if I'm not mistaken. And then this was certainly inspired by that. That was a paper about, reviving the conformal bootstrap in general CFTs, not thinking holographically. This is kind of a holographic branch off of that work. And so they established some results which went part of the way toward substantiating a conjecture which they made, which we stated a few times, and which Monica just nicely stated for us. There are a few different versions of this conjecture. There's sort of the one they literally made, and then there's the one that they were actually proving was true. Let me state the more general one, which is that if I have large central charge and a large gap in my single trace higher spin spectrum, then this is sufficient to guarantee the existence of a local ADS dual in the bulk. So these are the kinds of terms that they phrase this conjecture in. I mentioned this conjecture at the beginning of the course in slightly different terms, saying that these two conditions on the CFT side were sufficient to guarantee the existence of a bulk theory with Einstein gravity coupled to low spin matter. So let me explain a little bit what this language is about and where they were coming from. And then we'll talk about why this is significant and what they did to try to prove it. Okay. So local ADS dual means that if you go below ADS length scales, you can describe the bulk by a local quantum field theory interacting with gravity. So recall that in the bulk, if you have some effective field theory scale, and you take the ratio of LADS with that scale to some number, which is positive, then this defines some kind of dimensionless gap scale, right? And when this number is large, then the theory is weakly coupled. And if we identify this with the higher spin gap scale in particular, then it becomes a statement about the large higher spin gap. Okay. Useful for orientation, as usual, to think of this as L string. Then we have locality not just at the ADS scale, but all the way down to the string scale, where at strong coupling, right, this is just lambda to the 1/4. So if this were 1, then this is lambda to the 1/4. And at large lambda, say n equals 4 sub mils, right, this is big. What is the statement? The statement is in the bulk, it's gravity, not string theory. The string corrections are suppressed. That's a form of locality, right? When L string is finite, you have this finite size object, you take L string to 0, it becomes effectively a local theory that you can describe with higher derivative corrections to gravitational effective action. So this, yeah.
But doesn't it sound like you're saying that at scales above the AD scale, something where might happen? You want to say that even at L much more than LADS, you still have a local.
Yeah. Yes. So even in this regime, yes. So in this regime, you have locality down to smaller scale. I mean, you have locality down to to this scale by definition.
It sounded like somebody who doesn't know anything. It sounded like maybe there's something happening at the
No, sorry. Yeah, but yes. So this is really about some sub-ADS locality, as they called it. And this is nicely thought about in terms of some scattering thought experiment, which will subsequently still is being studied, where you have some boundary excitation. People see down here? Did I lower this? No. So if you send some particles in the bulk, which is more properly done with formulating some wave packets with some proper initial conditions in the boundary, and you have these wave packets interact, then there's some configuration where they meet in the bulk almost at a point. Parametrically, with respect to the ADS radius, it's at a point. So it's over some region which is much smaller than the ADS scale. And so in this configuration, the 4-point function, which we view as some function of Lorentzian time, here I'm drawing global ADS in Lorentzian time, and some other boundary spatial coordinates x, has a divergence. The divergence is reflected in the fact that there's some singularity if you tune these times and positions properly. And this singularity is known as the bulk point singularity, because from the boundary point of view, it's not an obvious kinematic singularity in a 4-point function. The obvious ones are those where in Euclidean signature you take two operators close to each other. That's this OPE singularity. There are also singularities where two operators approach each other's light cone in Lorentzian signature. But this is something else. And its existence is something you can infer by thinking about holography and sort of observe it in special situations in theories which have nice bulk duals. Nice, effectively coming down to this. But from the boundary point of view, it's not obvious. It's kind of unobvious Lorentzian singularity. It acquired this name, and the bulk part is important. So in section 2 of their paper, they kind of motivate thinking about this locality question from this point of view, pointing out that there are certain scattering experiments which indicate some extra amount of locality, which can be manifest in this boundary diagnostic as a certain special singularity. And their claim is that the only conditions in the theory needed for these types of singularities to emerge are these two conditions, which in bulk language amount to the statement that you have classical gravity, and that gravity is there's small curvatures everywhere. There's some effective field theory scale, which is maybe much less than the Planck scale, but it's much greater than 1. Okay, and let me remind, I've said this many times, but just to be clear, delta gap can be defined as the dimension, the lightest angle trace operator with spin greater than 2. Whenever we write spin j, we keep implicit that sufficiently high dimension, there are multiple spin quantum numbers, but this is a standard. You define a notion of higher spin even in that setting. So let's talk about why this is significant, what it implies, and then what calculation it is. So why is it significant? Well, first, it's highly reductive in the sense that all you have to do is fix this one spectral condition of your large C theory, and then the rest of the full structure of GR, perhaps coupled to some low spin matter, is supposed to follow from that. So if we think in CFT language, we have this whole set of dimensions and OP coefficients. And so in particular, our boundary theory has a stress tensor. And the stress tensor 3-point function has some coefficient, in fact, several coefficients, by which it's parameterized. And the claim is that when you have a gap in your higher spin spectrum, the 3-point function of the stress tensor takes a special form. But these two things are not a priori related. So one spectral condition fixes many correlators. In fact, the claim would be that any n-point function of the stress tensor, dual to the graviton, should at leading order reproduce that of general relativity in ADS. So that's not at all obvious from this thing. So basically what I just said. So you have an Einstein gravity sector, which means that all n-point scatterings of stress tensors are supposed to be that of Einstein gravity plus some corrections. And what are these corrections? They're down by some power of delta gap. So in other words, if you have some mass scale of some bulk effective field theory, which is valid below, so you have some bulk EFT, which is valid up to some scale m, which is bounded above by the Planck scale, but can otherwise just be some large mass scale, then the claim is that this is the scale of higher spin particles which have been integrated out, and that moreover, all of the higher derivative corrections in the theory are suppressed by this same scale in some way. The third thing, which is interesting and significant, is that there is a sharp distinction between low spin and high spin. And that's something that tells us maybe we should look out for interesting signatures of higher spin operators in CFT correlators. Yeah.
Is it so you start solving this large n, and then you simply see that the OBE coefficients to higher spin operators are down by delta gap?
So it's more than that. These are the OP coefficients of the low spin operators that are part of the CFT.
Okay.
But yes, morally, that's what one wants to show.
So they show this or?
No, this is what follows from the conjecture that this is or should be true. And now we'll talk about what they show.
Yeah, maybe you can say a couple of words. Maybe you're going to say it anyways about what do these conditions mean actually in CFT.
I will say this. Yes, I will get exactly this. You're anticipating the lecture very well. This is great. Your costume is enhancing your brain. Right. So, great. What did they actually do? So, they looked at a toy scalar level. So, just some scalar fields in ADS. And they established a one-to-one map between the following two things. On the one hand, the full set of 4-point contact vertices and some scalar effective field theory in ADS. And on the other, crossing symmetric solutions to the generalized free field plus perturbation. So for every bulk vertex you can write down involving 4 scalars phi, there is some crossing symmetric solution which addresses the generalized free field answer by some OPE data which corrects it consistent with crossing. I think it should be obvious that this conjecture is much stronger than that. We'll return to that. Now, there are 3 different ways to set this up. Let's say there are 3 equivalent ways to set this up. And so in ADS, you can imagine we have some Lagrangian for some scalar phi. The kinetic term d phi squared. And then we have some derivative expansion in chordic vertices. So we're just going to focus on 4.5. So we have some g naught phi to the 4th plus g2 4th d3 d phi squared d squared phi squared plus dot dot dot. So each of these g's is just some constant, some Wilson coefficient, if you like, in front of some higher derivative term involving 4 scalars. It's perhaps better to, instead of thinking of a bulk Lagrangian, which is subject to field redefinitions and things like this, to instead expand the chordic amplitude, which gets contributions from each of these coefficients. So there's some bulk, or some boundary 4-point function, A, B, and B bar, which would get its first contribution from this phi to the 4th term, before B naught. There's going to be some, let's call it A phi to the 4th, plus G2, A, B, phi to the 4th, plus G3, A, B squared, B squared phi squared. And each of these functions is some function of cross ratios, which after some experience is easy to compute, but it's not terribly easy to write down. But there's some d functions, because as we explained last time, right, for the phi to the 4th vertex, the definition of a d function is just the 4-point conformal integral of scalar propagators meeting at some point in the bulk. And these here are just the same thing with derivatives at the vertices. Okay. Now, a third way to write this is in Mellin space, which is especially useful for thinking about the HPPS conjecture. Why is it useful? Well, as we explained last time, going from position space to Mellin space is especially nice for chordic contact diagrams, because the Mellin amplitude order by order is just a polynomial in S and T. Whereas these are just slightly nastier, and this totally systematizes the expansion and make crossing manifest and so on. So, in particular, up to some constants, some numerical, some numbers, which would be d-dependent and delta-dependent, where delta is the dimension of this scalar phi, which I guess here is, I'm taking it to be massless, but this is just a constant, right? First one's just a constant. And the second one is a quadratic polynomial, because it's 4 derivatives. The third one is a cubic polynomial, because it's 6 derivatives, and so on. Let me define these invariants sigma 2, sigma 3. These are totally crossing symmetric permutation invariant combinations of ST and U, no doubt familiar from other contexts. Okay. And the fact that this goes like S squared is this is a 4 derivative term. Right? So the dimensional analysis tells you the order of the polynomial. Good.
Yes. Shouldn't the G's be weighted down by some length scale as well?
You mean here?
Yeah,
Yeah, I'm keeping that implicit, I suppose, but you're right. So there should be some
an EFT maybe.
yeah, right. Yep. So let me keep that implicit, but yes, they should be down by the appropriate powers of the EFT scale. I'll imagine that G is dimensionless for the sake of this type of formula, but yeah, that any factors left out can be just restored by dimensional analysis with respect to some EFT scale M. Thank you. Okay, and so now we get to the correspondence, like a boundary side, HPPS established. So on the CFT side, we are doing crossing at 1 over C, by which I mean correcting generalized free field. Right? There's no C here, there's just some scalar effective field theory, but these vertices are correcting some generalized free bulk action. So in that sense, it's a 1 over C problem on the boundary. And we're looking for solutions of crossing with double trace operators only, and support at this corrected order up to some spin capital L. Let me explain this. So there's some corrected amplitude. This is A1. Okay. And in terms of conformal blocks, one can write ansatz, which look like this. There's some correction to the squared OP coefficients. And there's some anomalous dimensions. Times the conformal block for the exchange of the N comma L double trace up. So O dual to phi in the bulk. And then here, this notation GNL means the conformal block for the exchange of this NL composite. Okay. So this is a derivative with respect to N because we have this anomalous dimension term. So this is what makes this the log Z in the cross ratio when you act on the block with it. Okay. So you have this as your ansatz for crossing, and then you say, let's take the spins L to be bounded above by some capital L. Now, why is this the right thing to do to solve crossing in correspondence with this order by order? Well, there's some intuitive way that I like to think about this. We have some scalar, say phi to the fourth in the bulk. So let's imagine first we have the phi to the fourth term near the S. This vertex carries no derivatives. It's just phi to the fourth. If you do all the hard work of decomposing this into conformal blocks, you will see that the only exchanges are double trace operators of spin 0. But you can anticipate this just by thinking about the diagram in the sense that if you imagine kind of resolving this context interaction a little bit and asking what are the spins of the operators that are supported by this vertex? Well, you have some two particle state coming in and two particle state going out. And here, because there's no derivatives, this must be a scalar state. And likewise on the way out. If instead you have some, let's take d phi to the fourth vertex. Well, now there's sort of one derivative on each leg. And if we do this resolution, we ask, what is the spin of the operators coming in and going out, where spin is captured by the number of derivatives? Well, here it's up to 2. So there's 2 derivatives on the left, 2 on the right. So there's a spin 2 exchange, which is possible. And likewise for all the higher derivative vertices. Let's do the next one. This is, I think, useful. And we'll stop. So the next one I wrote was d phi squared, d squared phi squared. So here there's, say, a d and d squared, d squared. And so even though you have 6 derivatives, that's not enough to make spin 4 exchanges. For spin 4 exchanges, you would need, 2 derivatives on each leg. And because it's a real scalar, we can't have a spin 3 exchange because of Bose symmetry. So this actually only hosts spin 2 and spin 0 exchanges as well. Okay. And that's reflected here by the fact that if we look at how many powers of s are sitting in these 2 terms, imagine fixing t and just counting powers of s. U is the number minus s minus t. So this goes like s squared, and this has 2 s's in it as well. So say if you want to ask in the t-channel decomposition of these diagrams, what spins are appearing? Well, then I would, fix t and then look at the powers of s. And this has 2 powers, and this has 2 powers. So each of these has 2 powers of s, which is the statement that only spin 2 or less interactions are included. In other words, that if you do a conformal block decomposition of this, you'll get composite operators of spin 2 or less, namely spin 0, because here we have Bose symmetry. Okay. So for any capital L, you are constructing solutions of crossing, which look like they should be dual to these corrections to a bulk scalar EFT amplitude at some fixed order in the derivative expansion. And that's actually what HPPS showed. And these solutions are in one-to-one correspondence. So back to HPPS, if we take Mellon amplitude to be constant, say G naught, then this maps onto the L equals 0 solution to crossing. In other words, you solve crossing for an ansatz like this, you get specific data here. Right? Remember, this generalized free field coefficient is known. You solve for these data, then you do a bulk calculation, you solve for the same data, and they match. If you do the next case, then this maps onto a specific solution of crossing where you take the maximum spin to be 2. And likewise for all the higher derivative terms. Good. So maybe I should have said this slightly earlier, a moment of dimensional analysis. So in general, so what is the general term here? This is going to be sum over indices A and B, some coefficients CAB, times sigma 2 to the A, sigma 3 to the B. So the dimension, right, so each sigma goes like s squared. The dimension is 2A plus 3B times 2, because it's S, right? So the mass dimension is 4A plus 6B. So these correspond to derivative interactions in the bulk with that number of derivatives. And the spin of any such interaction in any channel is bounded above, equals L, by 2A plus 2B. Okay. All right. So HPPS constructed solutions and matched them. They didn't do this for arbitrary L, but one thing they did do for arbitrary L is to count solutions on both sides and show that the counting matched exactly. I think the kind of explanation that I've given here almost makes that seem trivial, because once you realize you can formulate your correlator in Mellon space, you're just counting these polynomials, and the match really comes down to the fact that you're setting up the boundary problem right to capture this bulk problem, but the rest just follows quickly, because on both sides you're just manifestly writing the same types of terms using the same dimensional analysis principles. Yeah.
If I just start from the boundary, I mean, a priori, I don't know whether there's going to be local bulk interactions that produce that precise determinism. The counting the fact that the counting matches is a necessary consistency condition, but it's not sufficient one. Is it possible to run the argument like saying, okay, let's do the bulk calculation, it solves crossing by definition, and then somehow the solution has to be unique or the boundary in 1/n, and therefore this is the least?
Yeah, I think that still wouldn't. I think morally that is included in what they did. I mean,
I could write on some by local interaction or God knows what. You know, a priori I don't know that the CFT at large n needs to know about the counting is not suspicious. So there's some mathematics probably that.
Yeah, I agree, and this is why I think it was non-trivial, and especially once you graduate past scalar time models, then these calculations would definitely not be manifestly equivalent. Even if you just had a single trace exchange, you need to, so if you solve the bulk amplitude, decompose it into blocks, and then to show that there's some match, you'd have to set up a boundary crossing problem, which has a unique solution up to the same kinds of ambiguities that are present in the bulk, which is what one can do. But yeah, in both cases, their case or this more complicated case, you need to do more than just count. And so I think I agree that that approach won't ever tell you what's a sufficient condition for the emergence of the bulk from the boundary point of view. But yeah, I agree with what you said. And I think you can do the calculation this way.
And the more general thing with single trace exchanges, has it been done in the literature? Or?
Yeah, so I'll talk about it. But just for the counting for a second, so if you read HPPS, you'll see, I mean, we shouldn't stick too closely to history, we understand this result better, but you'll see that they say there are, let's spin L plus 2, L plus 4 over 8 solutions to this crossing problem with max spin L. This is easy to prove. It's especially easy when you think in this polynomial basis. So you're just counting the number of polynomials you can construct with the right properties. It's kind of amusing to show where this comes from. So I know it's simple, but it's still kind of amusing to do it. They didn't do it this way in the paper. So you have sigma 2s and sigma 3s, and you want to ask, okay, some fixed order, how many options are there? There's a generating function for that, right? The spin is increased by 2 for every sigma 2 or sigma 3 you add. The generating function is just 1 over 1 minus q squared. And you can write this as a sum over powers of q with some coefficients dn. And then if you sum little n from 0 to, I guess, L, you get this, you substitute n for L, and you get that result. So it's just a counting argument. So the counting is simple, but it's the construction of the solutions that really gives it some teeth. Okay. Let me erase this. Okay, so hopefully this convinces you that there's in some way, some derivation of the emergence of some nice bulk theory, where here nice is played by the fact that you're looking at a scalar effective field theory, which is a derivative expansion, by imposing the right conditions on your 1 over c crossing problem. But clearly it's just a toy model in a few ways. Okay, so what does one want to do? Well, ultimately we're interested in showing that you have gravity in the bulk and that it's Einstein gravity. And as we said before, this would amount to showing that under the conditions of large C and large gap, the stress tensor correlation functions, say the leading order connected, are those of tree-level Einstein gravity. Here. This is a tall order. This has not been done. Okay, this has been partially done. It's been done at 3-point level. We'll talk about that in a second. But for arbitrary endpoints, this has not quite been done, but there's no doubt that some version of it is true by now. And I would just point out that, say, on this side, if you say, I'd like to just take the formula in hand for ADS D plus 1 stress tensor endpoint functions, and then I know what I have to compare to, and I can try to do a computation. It's not that simple. So just as an aside, even at n equals 4, so the 4-point, this is not known fully explicitly in the bulk. So, yeah. We put unknown in quotes. It's complicated, right? Each stress tensor has some indices. It's symmetric traceless spin 2. It's a 4-point function. So there's a lot of tensor structures flying around. And first one needs to get a handle on that. In the CFT3 context, this is better understood. Once you go to CFT4 and higher, it's really quite wild, which is to say there's like many tens of tensor structures that characterize this thing. And so there's no simple answer even to compare to at 4 points. There's some kind of implicit answer in ADS5 CFT4, but it's not written in a form which facilitates easy comparison with CFT data. Yes?
Higher dimensions, does the TTOP close on a small number of...
Good question. No.
So this is why it's hard. It's not just indices. It's also that, yeah, so what does it give?
Okay, so good. That leads me right again. What I was going to say. Great. So the easiest thing here is to try to address 3-point functions, right? 2 points trivial. Let's talk about 3-point functions, and then we can ask about higher point functions, and we can use these to make 4-point functions. There's TTT, and there's also something like TTO, where O is just some spin J operator. Okay. The statement of HPPS is that this should be non-zero and equivalent to that which you would get from Einstein gravity. And if there are other corrections that can appear consistent with conformal invariance, they should be suppressed by this delta gap scale. And corrections like this should also be suppressed, because not only does the bulk have an Einstein gravity subsector, it's a consistent truncation. It's a closed gravity sector. So that means that correlators with a bunch of T's and one other field should, at leading order in this large n large gap limit, be 0 according to their prediction. Unlike 2 dimensions, this can be non-zero. Right? So for those thinking about CFT2 a lot, the TTOPE closes on itself. That means it's just composites of T. In higher dimensions, this is not true. So the stress tensor is a singlet under all global symmetries. So any O, which is a global symmetry singlet, can appear here. And whereas in 2 dimensions, the TTOPE is the statement of the existence of the Virasoro algebra, which is, closes just a set of currents, forms an algebra, with no other operators appearing. So this is an essential difference between low and high dimension.
Okay. So you're saying you have an infinite number of O's that
principle, absolutely. And if you look at the large N even finite coupling CFT, there is an infinite number. And then the claim, so what is the claim of HPPS? Is that this should equal the GR result in the limit we've discussed, and this should be 0. More precisely, suppressed by this very scale to some power, which, as we'll see in a second, is 2. Good. So the second thing that's left, where the HPPS didn't actually prove, is that the scale that suppresses higher derivative terms is actually the higher spin gap scale. Right? That was part of the conjecture, but it doesn't appear anywhere in these scalar calculations. It's just a scalar model. There are no other operators at all. So say the EFT scale in the bulk should be identified, or be equal to a higher spin mass scale of some higher spin particles, which is dual to this delta gap parameter. And also, finally, even not in the gravity sector, even in this scalar toy model, if derivatives are supposed to be suppressed by this higher spin gap scale, then higher derivative terms involving even scalars should be suppressed this way. So one expects the suppression of all higher derivative vertices, even those involving scalar fields. Whereas in the HPPS story, we just treated each vertex one by one, ignorant of the coefficient, and mapped them to solutions of cross. Okay. But clearly, they had good intuition about the problem because HPPS conjecture is invalidated over time, even though their model didn't capture all the features of their conjecture. All right. So a lot of the work in the several years after, understanding 3-point functions. First, this one. So let's say this was 2013, and this was 2017. So the stress tensor 3-point function was analyzed in a paper by Kamanho, Edelstein, Maldacena, Juboeda, aka chems. So we have HPPS, we have chems. Okay, those are things you can confidently say in a conversation with people. I didn't just make these things up. They have names now. So what chems did was to think about the gravitational problem and to show that the stress tensor 3-point function takes the form of that of Einstein gravity in this large and large gap. So from the CFT side, in CFTs in 4 or more dimensions, and basically in 3 dimensions up to some small subtlety I'll mention in a second, there are 3 tensor structures for this. So I'm suppressing the tensors on all the t's, of course, but they are there, and that means that the right-hand side will have some index structure. The permutation symmetry of this 3-point function, combined with the symmetric and traceless condition on T and the conservation condition on T, restricts the right-hand side such that there are 3 tensor structures. And you can write them in the following way, which anticipates holography. There's a term I'm calling the GR structure, the Einstein structure. There's a second term with some coefficient alpha 2, which I have with an R squared subheading, subtitle, index, what do I mean? And alpha 4 times some R to the 4th structure. Okay. This is a CFT statement, but I'm using this suggestive labeling because in a bulk theory, just if you write down Einstein gravity and compute the 3-point function, you get only this structure, not the other two. If you then add an R² correction, you turn on this structure, but not this one. And if you add an R³ correction, then you get this structure. And CFT tells you that there are 3 structures. So actually, from the bulk point of view, if you add higher derivative corrections beyond that, they don't turn on any new structures, but they will modify the coefficients in some way. But I could equivalently, perhaps less confusingly, written as just in some basis of tensor structures, which doesn't look anything like the bulk. Right? It's just a CFT statement. So I want to emphasize this. So.
And I think you mean very specific combinations of the Riemann.
Let's see. I don't think I
mean, Riemann squared is probably different from Gauss-Bonnet, no?
let's see. Yeah. I actually don't think that's true. They change this, but they don't turn on a new tensor structure.
Any R squared, whether I construct from the Riemann, the Ricci, or the Ricci scalar, is going to give me.
I believe that's true.
Even Gauss-Bonnet?
I think so. Wrong. Right, so in ADS5 and higher, Gauss-Bonnet is not topological. So it's restricting to that case. So yes.
Yeah.
Even if it's topological, it doesn't mean that they. I don't know if the contribution is 0, but it still has about the contribution, so in principle it can be still affected. Even if.
Yeah. No, indeed, because you're varying 3 times anyway. So, yeah.
And you're saying the same statement was for R cubed.
Yeah. Yes. Provisionally, this is true. Yeah, I'm pretty sure this is true. Yeah, how could it not be? Okay, so what one wants to show is that these coefficients are suppressed in this large gap limit. And so what Kems showed is that indeed alpha 2 is bounded above by 1 over delta gap squared. 4 is bounded above 1 over delta gap to the 4th, which is what a bulk dimensional analysis would suggest if you take my word that these structures are associated to these higher derivative bulk terms. Kems did a bulk calculation, in fact. So where did these things come from? So let me put these in a box.
Is it possible to put further constraints on this alpha 2 and alpha 4? Like at high energies, you would like to have Rayleigh growth or things like that? Okay,
there will be more precise bounds, indeed, but they just pin down, say, a numerical coefficient here. Yeah, I'll quote that in a second. Good. So let's say we'll take a break in 5 or 10 minutes, by the way. So, all right. So what did Kems do? I won't spend too much time on it because I want to cover some other material. So they did a bulk causality experiment involving gravitons traversing shock waves generated by other highly energetic gravitons, and showing that there's a time advance rather than a time delay for the particle traversing the shock wave unless these conditions are obeyed. So imposing causality in the appropriate way leads to this condition. The leading order in large gap, right, these have to be 0. So that's what the first thing they established, that for any non-zero amount of these extra structures, you will violate causality in a kind of experiment like the one I just described, in some controlled way at some length scale, which is within the regime of validity of the causality experiment itself. And the way to fix this is to kind of cut off the causality violation by introducing some small correction from some higher spin particles that have been integrated out of the theory and which lead to these suppressions. So if you say the coefficients of these troublesome higher derivative terms were determined by integrating out some infinite tower of higher spin particles, then this can resolve this causality problem. So there are two things about this which are interesting. The first is that you get the powers consistent with dimensional analysis in terms of the sort of effective field theory scale, and they show that the effective field theory scale has to be a higher spin scale. There needs to be some infinite tower of massive higher spin operators, which fixes this low energy problem for you. And that's what leads to the appearance of this delta gap. So it's vital in this result that it's the higher spin scale specifically. Now, this was later proven in CFT by setting up a kind of analogous problem in some work by Hartman and collaborators. And so at this point, this is something which is established on both sides, where this is a parametric inequality.
Reminds me a couple of
Yeah. So they looked at a kind of Lorentzian regime of a 4-point function involving stress tensors. And I think they looked at a TTOO correlation function, if I'm not mistaken. And they looked at it in the Lorentzian kinematic regime, which basically mimics the bulk setup that Ken's had. They showed that if you do this to this 4-point function, then you get some violation of the chaos bound if you don't have a suppression of these coefficients. Mention the chaos bound in the second half of the lecture. Yeah. So these kinds of things end up, you get into a situation where there's some polarizations to play with of the bulk graviton. So you have some formula for the time delay, which involves polarizations and this coefficient. And you see that there's always some choice of polarizations which can turn the time delay into a time advance. This was the chem's point of view. So the spin is important. It's important that it's a spin to particle which has different polarization choices. And at the boundary, this manifests itself in the fact that you have multiple tensor structures in the 3-point function. Like a scalar 3-point function is just a number. So that's kind of the mapping between these two features of the bulk and boundary. Now, recalling something from the earlier lectures, in 4 dimensions, alpha 2 is maybe up to some number. The magnitude of the ratio of A minus C over C. So this leads to one of the more famous results of the chem's bound, which is the 4-dimensional application for alpha 2, which is that A minus C over C is bounded by 1 over delta gap squared times some positive order 1 number. And this is something that I alluded to at the very beginning, and it's an interesting result. What do we learn? If you want a bulk theory, which looks like GR coupled to low spin matter, then A must equal C at large C. The right-hand side is 0. Right? So large gap, A approaches C. We saw in N equals 4 superior that A equals C as a function of N equals 4 superconformal symmetry. We have these Hoffman-Maldacena bounds where A over C is bounded by order 1 numbers above and below, but it always includes A equals C. And so A equals C is uniquely specified by this large gap condition and this inequality. So it's a leading order statement. Okay, they don't have to be exactly equal, but at large C, they must approach each other. And we take this large C, large gap. on the other hand, if you have some theory where, right, so even in n equals 4 supergrowing wheels, if you have finite delta gap, so you're at finite tooth coupling in the planar theory, right, the right-hand side is finite, but of course that's consistent with A equals C. In other words, A equals C is a necessary but not a sufficient condition for the emergence of a simple bulk theory. There are plenty of theories where A equals C, a leading order in large C, or maybe exactly, which don't have an Einstein gravity dual. But it's the reverse, which is true. For all theories which have a large gap regime, A equals C in large C. Now, more recently, this was actually improved. So chems derived this parametric bound, which is very important in the development of the subject. More recently, using some functional methods in S-matrix bootstrap. I'll say a little bit more about this after the break. This was turned into a sharp numerical bound. So it's parametric in delta gap, right? You're still taking a large C, large gap limit, and so there's some number you can attach to this. It doesn't really qualitatively change anything, but it's good to have a sharp bound, of course. And this is not optimal. It was extracted from numerics. Perhaps it can be pushed further, but it doesn't change the qualitative picture which I'm trying to convey. This is some more recent work by Lee, Martinez, and stuff. Yes.
So here, I mean, we don't just need them to agree at large C, we also need them to agree at large top coupling, which is what controls delta gap.
Yes, in general, yeah. So if you have an SCFT, they don't depend on the coupling, and in a non-SCFT, we don't. Examples, but yeah. So in principle, what you say is true, right? Absent supersymmetry, where. Okay, let me say a little more about it. Yeah, one reason this is slightly unsatisfying is that we don't have any example which even gets parametrically close to this bound. So here, remember now we're in 4 dimensions. So in an SCFT, A and C don't depend on exactly marginal coupling. Let me use notation from previous lectures where T is some exactly marginal coupling. And delta gap can be viewed as an abstract proxy for a coupling. Right? It's the thing that, as you tune an exactly marginal coupling, you can go out to a regime where everything becomes strongly coupled. And absent an actual exactly marginal coupling, delta gap is playing the role of that coupling, which makes a gap in the spectrum. In the setting where you actually have one, A and C don't even depend on delta gap. So what that means is that in this SCFT setting, right, the right-hand side depends on this coupling, left-hand side doesn't even depend on it. And consequently, in constructions that have holographic duals, A minus C over C is suppressed by some power of 1 over C, where this number typically is either 1/2 or 1, which is much smaller than 1 over delta gap squared. Nevertheless, just from this totally general holographic point of view, I think we expect this to be the optimal bound in the sense that delta gap is really, in general, capturing this bulk effective field theory scale. But to actually make it sharp, to show in an example that it is a sharp bound, requires non-supersymmetric tools that we don't seem to have yet. But I think it's, this is sort of the right bound for general holography, but it's hard to try to saturate it in practice.
Does it come close to saturating like M theory examples where C and delta gap are controlled by the symptotic?
Well, that's not really That's a bit outside the regime of validity of this result, actually. This is a classical result. That means you're just looking at tree level in the bulk. And so what you're on firmest ground in stating this when you have two independent scales, C and delta gap. But if it's an M-theoretic case, then yeah, I'd have to think a little bit more about that.
It's not something that's like done right away, that like we compute some scattering amplitude in M theory and we can see which tensor structures are suppressed by or so. I mean, it's not immediately apparent.
No, I don't think so, but yeah, I don't think formally this result as stated here is even valid in that case. Sometimes you can see in the M theory cases, you have loop effects end up mixing with higher derivative effects in the 1/C expansion. At low orders, before this starts to happen, you can get lucky. So, for example, like a one-loop correction to supergravity as a compactification from M theory will go like 1/C squared. So if you're looking at some higher derivative effect, whose dimension is such that when translated into field theory variables, it goes like power of 1/C, which is less than 1/C squared, then you can talk meaningfully about that at the classical level, a correction to the classical theory. I think here actually this might be in that category. So we're just talking about R squared, say. But I don't think about whether the suppression matches. So let's see. Yeah, let me get back to you.
You will require a weakly coupled EFT until the EFT cutoff scale.
Does this require that?
Yeah.
Okay, so the chems result. Yes, it does. And in these more recent papers of the sharp bounds and stuff, yes, they are. That's the definition of the EFT scale. So the M theory case is outside of their realm. But in the chems setting where less is being used, I think yeah, that is also being assumed. But still, you might be able to push the bound in that regime. So for this 23, for example, that's being assumed. Okay, yeah, we should take a break. But let me. Okay, well, we're a little bit over time in the break. I guess we should take a break. I'll make another small comment afterwards, but you know what? Sorry, I'm going to make it now. It's going to take 1 minute. Okay, the TTO story. You can play similar games on the boundary side or on the bulk side, and you confirm this. Okay, so you confirm that it's suppressed by 1/delta gap squared. What is the bulk intuition for this? Well, you ask, what is the first vertex that can even give rise to a 3-point function of TTO? Let's take O to be a scalar and two gravitons. The first bulk vertex in a Lagrangian which can give rise to this is a Riemann squared or Weil squared by interaction. So how many derivatives is this? It's 4 derivatives. So if this EFT delta gap picture holds, you expect this to be suppressed by 2 powers of delta gap. And you can show rigorously from the CFT that it is. All right, so let's pause and continue in 10 minutes.
So we are online.
Okay, thanks. So we've got 45 minutes or something like this. And let's take stock. So here is the list of things suggested by this conjecture. We talked a bit about this one. And we talked about some of the evidence for this general statement, which is borne out in all studies that the bulk effective field theory scale can be viewed as this higher spin scale. Suppression of all higher derivative vertices, though, this we'll talk a bit about next. let me first ask if there are any questions about the first path. Stop slightly promptly. I guess I want to make a small comment, which is that these results are dimension independent, at least above d equals 2 or d equals 3 in this case. Here we're focused on the 4D case because we can talk about central charges, but in odd dimension, these alpha 2 and alpha 4, they just can't be written in terms of other data of the theory, but they're, if you like, independent intrinsic constants, which are bounded like this. All right. So more recently, there's been some work on constraining vertices in bulk effective actions. From this point of view of, on the one hand, applying functional methods inherited from the conformal bootstrap and the S-matrix bootstrap to S-matrices that describe processes in ADS space or in flat space, and on the other, this effective field theory community that maybe for model building reasons was thinking about trying to constrain effective actions using bootstrap principles like positivity and so on. And so now we'll talk a bit about this. And we've been led to it from a slightly different point of view, where we're trying to substantiate this HPPS holographic conjecture. And so it should be true that, say, scalar high derivative interactions are also suppressed by this scale. So there's a bit of a history here too, which is interesting. We'll talk about some of it. So you might like to ask whether the d squared 5 to the 4th correction, which is 8 derivatives, is suppressed by to the 6th, the higher spin scale. Okay. Now, one tool that's been used for this purpose that predated some of the more recent S-matrix functional methods is something known as the chaos bound or the Regge bound. These are basically the same thing. In some cases, they're literally the same thing. So the Regge limit is a certain high energy limit. In the CFT language, it's a certain kinematic limit of a 4-point function. In ADS language, it's a certain high energy scattering process that takes place at impact parameter. So let's like this. Okay. So here in this is sort of ADS side. But it's a limit we can take of some CFT 4-point function. We can think of it as in the following way. Let me draw this a little bigger. So this is our conformal compactification, and we have 4, say, space-like separated operators. Is this big enough? Let's call them 1, 2, and 3, 4. You can start moving these operators around. So they're all space-like separated. If you then take them to be light-like separated in folds, so we sort of take these operators and then take 4 to approach the light cone of 1, and likewise take 3 to approach the light cone of 2. Sort of a 2-step process, which you'll see in a moment why I'm thinking of it as a 2-step process. So we have 1 and 2 here, and 4 and 3 here. So now 2 and 3 are light-like separated, and likewise for 1 and 4. So we're no longer in this Euclidean kinematics we started with. And then from here, we can take them to infinity in a certain special way, where 1 and 2 become light-like separated as you approach asymptotic infinity in some controlled ratio. And likewise for 3 and 4. So you sort of take them to approach each other's light cones as you take them to infinity. And this is the Regge limit in these causal terms. Now, if you're taking some CFT 4-point function, J to Z bar, you want to take this limit. And this was all very nicely explained in a paper called Conformal Regge Theory by Costa, Penedonis, and Gonsalves, I think. Emilio's nodding, so I feel confident. Good. So how do you do this? So you start with your A of Z and Z bar. So you start in Euclidean, but then you take Z and Z bar to be independent complex variables. And first you take Z bar around 1 with fixed Z. Okay, so you move Z bar around 1, keeping Z fixed. And then you take Z and Z bar to 0 and some fixed ratio. So given some 4-point function, you can do this. And the claim is that in this limit, the leading order behavior, the Z and Z bar go to 0, gives you the Regge limit of the correlator. In general, this limit will be singular. There'll be some power of Z. Or you could ask whether it's singular. There's going to be some characteristic scaling with Z. You can ask whether it's a singularity or if it goes to 0. We'll talk about that in a second. But this is the procedure on the boundary for how to access this Regge regime. And this is dual in the bulk to, so let's draw a picture. So what does this look like in terms of some bulk scattering process? You have some boundary operator like this. And you have them approach each other separated by some distance, which I'll call B, the impact parameter for the bulk scattering, which is something which you can dial, which is held fixed. So you take a high energy limit in which this B is held fixed. It's up to you what it is. And this is the bulk scattering process dual to this kinematic regime of the CFT correlator, the Regge limit.
Can you explain how you went from your diamond picture, so they conform to the light cone of 1 and blah blah, how they gave you those 2 steps in the system?
Yeah, so I'll try to explain. That's why I wrote this in 2 steps, actually. Okay, so the first step, you're crossing light cones.
Yeah, can you remind me what is that in terms of these cross ratios?
Yeah, so that's this step. So when you take Z and Z bar to be independent, and then you actually take Z bar around 1, you're passing through some branch.
I was thinking of reaching the light cone means standing
Yeah, so it's like, but then you pass through it and come back, and now you're inside the light cone. Yes, exactly. So passing when you hit the light cone, you're like just going through the branch cut that starts at 1, and then you pass through it, and then now you're inside the light cone of the other operator. And then once you're there, then you can take them to approach each other. But so 1 and 2 are becoming light-like separated, but in this way where they're both going to infinity at the same time. If you were on the first sheet, if you hadn't done this first step, then Z and Z bar to 0 is just the OPE limit, where they're really coming close like this. But after doing this, you take Z and Z bar to 0 with some fixed ratio. Now they're becoming light-like separated like that. That's the cross thing. And there's a bound on the Regge scaling of CFT correlators, which is useful for constraining ADS effective actions. Okay? And the bound is actually that for a finite central charge CFT, this limit must actually be finite. So when you do these steps, your 4-point function, the 4-point function must decay. So the power of z must be non-negative. However, at large C, the Regge limit and the large C limit don't commute. And the leading order in large C, a connected 4-point function, can have a divergence, but the degree of the divergence is bounded. And if you're familiar with the chaos bound, that bound is the same thing as the upper bound on the Lyapunov exponent of some out-of-time ordered 4-point function. So if we parameterize the limit of the 4-point function like so, let's write this as not for historical reasons, then the claim is that so there's going to be some time-some function of the fixed ratio z over z bar. Is that in a non-perturbative CFT, that is a finite central charge, J naught is bounded above by 1. But in a planar CFT, so if there's some overall 1 over c in front of here, where this is the connected correlator, then J naught is bounded above by 2. And this 2 is the spin of the graviton in ADS, aka the spin of the stress tensor. In other words, when this is saturated in a planar CFT, you're in this gravity regime, where the Regge limit of the 4-point function is dominated by the stress tensor exchange. Indeed, if you ask, how does a single conformal block contribute to the Regge limit? We take the block G delta J bar Regge limit. This goes like z to the 1 minus j. So in general, you will have an infinite sum over conformal blocks. You take the Regge limit, and there's some resummation happening because that sum involves an infinite tower of higher spin operators, right? These limits don't commute. If you do that, if you have the full 4-point function, then this growth must actually be bounded such that it decays. Even if block by block there's a growth for sufficiently higher and higher spin. In a planar CFT, though, what happens is that, well, you have single trace operators, spin bounded above by 2. So the single trace contributions are consistent with this, operator by operator. There's a finite number of them. And then you have all the double traces, and with some work, you can show that this infinite tower of double traces also resums to give something which doesn't exceed 2. So in the end, the Regge growth in a large N large gap CFT saturates this bound. In general, J naught is a function of delta gap. Okay. So let me actually, let's see. Let me say it some more clearly over here. So, right. So some intermediate result. This thing interpolates between 1 and 2 as you dial delta gap. When you take delta gap to 0, this is like going to a free limit, and you land on some free planar correlator. as you increase delta gap, you go to large delta gap, it interpolates from 1 to 2. So a nice example here, of course, is given by thinking about n equals 4 super Yang mills. This quantity is a function of lambda, and this J naught notation comes from the fact that this is the red J intercept. We can think of the operators in the theory as living on trajectories, like we talked about in the first lecture. This J naught is where those trajectories cross the y-axis. But for now, we can just think of them as parameterizing this red J growth of a correlator. And this thing is some quantity, right, which interpolates between 1 and 2. And there are some exact results for this from integrability as a function of lambda. There's some papers I mentioned in the reference list where you can find some really nice plots. And I'll just refer you to that for some more details. But you see very nicely this asymptotes to 2. But that fact, you don't need all the power of integrability to see that. It's just something you can understand in more general grounds. There was also a paper by Brouwer, Spencer, Polchinski, and Tan, which thought about this from a bulk ADS perspective. And okay, so there are some comments about the red J growth.
So when you say that the J0 is smaller or equal to in a non-perturbative CFT, that's proven?
Yeah, that was proven. Yeah, good. So that was proven by Karen Huo in his analyticity and spin paper. The idea is that, yeah, when you do this first step, going on to the second sheet, you can show that the correlator is bounded above by its behavior on the first sheet. And what that means is that in the second step, when you take z and z bar to 0, the behavior must be bounded above by the OPE limit, which is what happens when you take z and z bar to 0 on the first sheet. And that, pulling as an appropriate factor, is non-singular. It just, you get 1. So the red J limit is bounded above by the OPE limit, which appropriately defined is finite.
So this result of the interpolation in 1 and 2, can I think of it as just how much the planar truncation captures of the full CFT versus, so it captures very little at strong coupling and almost all at weak coupling?
Interesting. Maybe with the caveat that at strong coupling, yeah, it's a bit like saying that the strongly coupled theory has many operators which decouple entirely. So in that sense, I think yes. Yeah, you're further away from the non-perturbative bound. So in order for that to be restored, you need to include lots of stuff which is not part of the Leibniz theory. I mean, there are two types of corrections to that too. Right? There's 1 over delta gap corrections, and then there's 1 over C corrections also. And if higher orders than 1 over C, the violation of the non-perturbative bound gets worse and worse. So, for example, if you look at like a one-loop ADS diagram involving gravitons, this has like red J spin 3. So it gets worse and worse in 1 over C perturbation theory, but then resum such that a finite C, it's okay. So yeah, I think in some sense you can. But
I think that if I correct my blinder CFT, it's going to look worse and worse. And
yeah.
So this doesn't look too bad. If I'm in the first approximation, then it's going to look worse and worse, and I really need to resum it to make sense.
Yes. But it's kind of in a dumb way that it gets worse and worse, because at higher orders in 1 over C, you're not introducing new operators that aren't composites of the old operators. So like this extra dilation just comes from the propagation of composites of stress tensor. And so, yeah. So the planar theory really captures the leading interesting aspects of the large C limit that deviates from the finite. Is there a question? All right. So why is this useful for the constraining and bulk effective actions? Well, perhaps it is clear. Yeah.
Like, do we know explicitly that we can resum the 1/c expansion and get j less than 1, or is it something, a conjecture, let's say?
No, this is proven.
No, I know that
So-
that is proven.
This must be true for any good sequence of theories that has a planar limit. What was the question?
Like, if we take a planar CFT and we do 1/c corrections, as we were saying, then of course we expect that as we resum the series, we should get j0 less than 1. But like, is it possible to do this explicitly? Like, for example, do we know if we need some non-perturbative effects for this to give j0 less than 1? I guess so, no? Because the 1/c expansion is asymptotic.
Often it is. So yeah, you'd have something like, well, I mean, in the 4-point function, you have 1/c. So at planar level, you have your 1/c, and then 1/z, right? That's spin 2. And again, 1/c squared. And 1/z squared, I think. It doesn't always, after this order, it doesn't correlate like this. And so I think in the 2D context, there were some calculations by Fitzpatrick and Kaplan which tried to get at this. One thing they definitely showed was that it's a little tricky because this thing, so J naught itself can get corrected in 1/c. So if you think of this as like 1 plus a 1/c correction, there will be log z's appearing in higher orders than 1/c and to arbitrary orders. This term is sort of a different nature, and it's true that they all would be part of the resummation, but I don't immediately know what is required to get back under here. There might have been some study of this in the 2D context by Fitzpatrick and Kaplan.
It just it's Patrick and Kaplan, it's not.
They had a paper, the two of them, Chaos was in the title, maybe? And then some follow-up papers with some collaborators asked about this resummation to higher orders than 1/c. I think part of what they were interested in computing the 1/c correction to this 2 in a strongly coupled holographic 2D CFT. But they must have had to contend with this whole set of terms. So maybe one should look there.
Do we expect to have this kind of range of bounds in other correlation functions, like 6-point functions, 8-point functions, which is like 3 to 3 or 4 to 4, or even in 2D CFT, if we have like correlation function, some Riemann surface, and then somehow we take some Lorentzian regime. Let's take the 6-point function.
Some version of these bounds should exist, I would think.
Right. So in that case, you have more cross ratios, and then you try to pass to light cones, trying to create similar limits like this, and then ask what is the limit and what's the relative limit of the correlator, and then try to derive. Maybe the positivity constraints do not work the same as the 4-point function, but and then maybe in the planar limit there is some violation.
Yeah, I agree with everything you're saying.
Okay, yes.
Maybe someone in the audience knows this story for if people thought about this for 6-point. I mean, there's also you use factorization into lower point amplitudes to your advantage somehow. But yeah, with the more points, you get more cross ratios, and definitely there are different. Yeah, so this whole story in the S matrix community of multi-Regge limits for endpoint functions. where you take sort of sets of sequences of nested limits, if you like, where pairs of particles are becoming highly energetic with respect to each other. You have lots of different pairs, and so you can nest this in different ways. But yeah, I think the term here, one term here anyway, is multi-Regge limits, where people have studied this in the context of amplitudes for like 8-point functions. Not in the context of CFT correlators, aka ADS amplitudes, so much though. So yeah, this is coming back to me a little bit, but yeah, I think the point is that there's something to learn from the amplitude side, and this has been studied comparatively less on the CFT side. Yeah, good question. I think, in 20 years, we'll like look back on these times and say, oh, we were like so young, we're just dealing with 4-point functions. Do n-point functions. But I don't know. I don't want to be the one to like lead the endpoint revolution. It has to be stuff. But it's definitely interesting because exciting, and I think someone with the right temperament should do this. And some people are doing it, to be clear. Some people are studying 5 and 6-point functions, step by step. Blocks, n equals 4, places where you have a bit of a simpler problem or a bit more of a handle on it. Yeah, even in the context of out of time ordered correlators for higher point functions, there's some work by Anus and Hale and so on. Yeah, so I think none of these references are in the list I sent for the course, but they're out there. Yeah, I think I just mentioned the ones that I'm aware of. So speaking of corrections, I mean, one thing that people have studied is the sort of 1 over delta gap corrections to this. Okay, but let's turn to what this does for us in terms of constraining holographic CFTs, bulk effective actions. Yeah.
That computing the corrections of the biorder with higher divergence.
Yeah, so that's like not 1 over C perturbation theory. That is some kind of stringy, contending with the stringy effect, where stringy, that's the delta gap scale. So you're no. So it turns out that if you were to compute this doesn't just come from looking at some R² correction to the effective action. It's involves an diagrammatic resummation. Yes. So there are, let's say, in the n equals 4 strongly coupled planar n equals 4 context, this has been determined. In this paper by Brouwer et al., they give a bulk picture for how to compute this, which is friendly but not very stringy. And yeah, so it's a different kind of resummation, but it's a classical calculation. Okay, so finally, how does this help us? Well, hopefully it's a little bit clear. So if you have this bound on a planar correlator, and then you start writing down some arbitrary high derivative terms in the bulk, if those terms individually violate the Regge bound, then they can't be in the bulk unless they're accompanied by some infinite tower of higher derivative terms, which resum to be consistent with the bound. Okay. So in a scalar EFT, we can ask which terms are consistent with this bound. Right? So this is a spin 2. This is spin 2 growth, and we said that. Right, so these quartic vertices can be characterized by the spin, which in turn is a statement about not just the number of derivatives, but also the particular combinations of S and T that appear in the amplitude. And we can associate a spin with each of these sigma 2 and sigma 3. Sigma 2 was like spin 2, because it went like S squared, and sigma 3, also spin 2. So what this means is that the phi to the 4th, this is a spin 0 interaction. If you take the Regge limit of the correlator, you get Regge growth of spin 0. That's what that means. So this was B naught. This was B2. In part of the fourth, that's spin 2. B squared, B squared phi squared. This was B3. So this was B2 sin 2, B3 sin 3. These are all okay. These all have spin 2. So you can have these in some low energy effective action. This one's a little peculiar. It has 4 derivatives. You might think it's suppressed by this gap. Sorry, 6 derivatives. And this has 4 derivatives. You might think these are both suppressed by this delta gap scale. This argument can address that. But what it can tell you is that any higher derivative vertices must be accompanied by some infinite tau. Otherwise, they would violate this bound. Okay. So for BK, beta 3 is not allowed unless there's some infinite tau.
So you're saying that G2 and G3 are arbitrary for this company?
Yeah, the Regge bound can't constrain them.
Because, I mean, just from matrix arguments, I thought you could constrain at least the coefficient of d phi to the fourth to be positive and stuff like that. So
You don't have to say that. No, you're on fire today. Not just your head. All right. So, great. But forgetting about those, yeah, so the Regge bound can't constrain these, but it tells you that if I take this HPPS point of view and just add some chordic interaction in the bulk, I can't do that if it has sufficiently number of high derivatives unless I add some infinite tau. That's already an interesting result, which was sort of immediately implied by this chaos bound, this Regge bound. Good. So the second is slightly more sophisticated. So, well, okay, sorry. So this is just, well, I don't know what to number this. Let's just say 1A. These functional methods for matrices. So for these guys, they actually can be constrained. G2 and G3 are mutually constrained. So there are different versions. One of them predated these functional methods. Let me call this simple. It's actually a precursor. So if you turn off gravity, then there's a simple bound from the chaos bound, in fact. Right. What is the bound? Well, I didn't tell you the full story here. In a planar CFT, the Regge intercept is bounded by 2, but also the sign of the 1 over z term is constrained. It must be sign definite. So let's say that a Regge C goes like a number over z, and some appropriate convention, this must be negative. If you read the chaos bound paper by Schenker Stanford, and you think of this as the chaos bound, this is the statement that chaos decorrelates rather than enhancing correlation. So this gives a sign constraint and any purely spin 2 interaction. So now we go here. If you turn off gravity and just add a G2 interaction, this was this d phi to the fourth, so this says spin 2, right? Then this actually must be sign definite, and some conventions, negative. In fact, for what's about to come, let me say positive. Good thing I covered myself with some conventions. Now, there are some more sophisticated modern bounds, which involve gravity itself. So instead of in some scalar toy model, now we say we have a gravitational action, and we have terms like these d5 to the fourth and so on. Can we constrain these coefficients, G2 and G3? And you can. So where's the best place to draw this? Maybe here. So can people see this? Maybe it's not the best place. It'll work. If we make a plot of G2 and G3, right, then for G2, for example, it had to be positive without gravity. You turn on gravity, and what do you find? And this is in the work of Karen Huo, Mazach, Rastelli, and Simmons-Duffin, in this sort of series of papers about sharp boundaries for the swampland. The bounds depend on the spacetime dimension D, but in all dimensions, they basically look like this. This green region is allowed. And so you see that G2 is now allowed to be slightly negative, but in conjunction with some bound on G3. Right? So this cone region is allowed. That's a rigorous result from imposing crossing on an S matrix in a theory like the one we're describing here, gravity coupled to a scalar. And it's an interesting quantitative output from this S matrix bootstrap program.
So if you don't have gravity, is there a bound on G3 or?
Right. If you don't have gravity, there's no bound on G3.
So this, so should I think of this as being equivalent or just a sophistication of the older method, relation method?
Yeah.
And is there some relation on the strength of the bounds? Like, is the bootstrap bound always are the chaos bounds included in the bootstrap bound or the?
Not exactly, because in these papers, they consider higher and higher derivative interactions for this scalar sector. And they get bounds on those higher couplings, but the bounds are not of the nature that you must have an infinite tower of couplings above this. At least not directly. What they establish is that these so-called two-sided bounds in these coefficients show you that the scale by which they're suppressed. So this is a kind of dimensionless combination which I'm plotting here. I should have said that, where you've sort of pulled out this the appropriate powers of this effective field theory scale, N CFT. In a work by Karen Huo, Lee, Perlmutter, Simmons-Duffin, they show that this EFT scale must be the higher spin scale, and then with their bounding on the order 1 coefficients in the numerator. So they showed that you need to have this higher spin scale suppressing all the higher derivative terms, but they don't manifestly. The algorithm doesn't manifestly tell you need to have an infinite tower of them that resounds consistent with that.
So they're really complementary bounds.
Yeah, they're complementary. And then once you buy into the point of view that the EFT is controlled by the higher spin gap scale, then you should write down all of the terms suppressed by higher and higher powers of 1 over delta gap. And if you want to get the answer in that limit, you can't truncate your bulk Lagrange.
So can I think of this bound on the gravitational bound on G2, which is more allows a region that is not allowed without gravity, as a quartic coupling version of the BF bound for the mass of a scalar in ADS? Like that would be like a bound on the coupling of phi squared, while this is a bound on d phi to the 4th.
This is actually a flat space picture.
Okay.
The ADS version turns out to be essentially the same, but what I wrote is a result which is valid in both. So I think not really.
And also, I think there was a comment or a question about without gravity. I think the bounds they also do it without gravity as well. So you still get this same bound, just that it's positive. G2 is positive, but you still get bounds on the ratios.
Yeah, right. Indeed. Yes. physics is this like it's
Yeah,
what's
it's
it shaped? Oh, trin paper.
yeah, but also a bunch of there are two other papers getting similar concept.
Yes, indeed. I mean, there's a bunch of papers here. Yeah, thanks for pointing that out. It's important. Okay, so we are down to the last 5 minutes or so. So let me highlight some of the interesting questions that I think are open here in general dimensions. I've tried to emphasize the questions throughout the last 4 lectures, maybe as much as the answers. So hopefully by now you already have some idea of what some of the interesting questions are. One thing we haven't really talked so much about is, well, okay. We talked a little bit about this at the beginning, this idea of string universality. This would be nice to understand better, to substantiate from a planar CFT point of view. What is the statement? It's that, at least say in the classical limit where we know what we're talking about when we talk about string theory, all consistent bulk theories of quantum gravity. Maybe you want to add an ADS to that statement, are really string theories. A stronger version is that outside of the classical limit, this should be true. And we talked a bit about the organization of operators into regular trajectories, which is some kind of thematic version of this, which is true in all CFTs. And the emergence of universal physics at large gap is always consistent with the kind of stringy picture, but certainly doesn't imply it. It would be nice indeed to try to say something proper about this question. We've talked about it a little bit, so I won't say more. We also haven't talked about any finite temperature physics. And part of the reason is that I'm not sure there's enough material to give a course on holographic bootstrap at finite temperature, because the bootstrap has had relatively little to say about finite temperature physics in ADS, and definitely not much to say about black hole physics, at least not in ADS greater than 3 dimensions. And this would be a clear frontier to try to push, whether that means talking about thermal correlation functions and understanding their structure better, say deriving conformal blocks for them and drawing new consistency conditions, analogs of the Regge bound for thermal correlators, understanding better their analyticity structure in the complex frequency plane, and the emergence of interesting thermal singularities at large gap, kind of analogous to the bulk point singularity for vacuum 4-point functions. These are all things that have been touched on by some work so far, but they're still definitely not a big insight that the conformal bootstrap at large N has had for something like black hole microstructure. And finally, there are many interesting questions that I like to think about regarding extra dimensions and the possibility of the consistency of theories of pure gravity in various dimensions. And slightly more generally, the question of whether there exists scale-separated vacua in ADS. This is something that you can try to formulate rigorously from the CFT side and then try to answer it. And there's been some work formulating this question with some rigor. But answering it is another matter. This has definitely not yet been answered. What is it that hasn't been answered? What is the question? The question is whether you can have these ADS times small solutions of a consistent theory of quantum gravity, where you can narrow the scope a little bit and ask about string theory. Still, we don't definitively know the answer. But the bootstrap is a set of techniques that should be well suited to addressing this question. because bulk approaches are necessarily complicated because you're dealing with modified string theory or quantum gravity, because you need the ingredients that transcend the supergravity limit in order to make small curvatures consistent with whatever the field equations are. And it's hard to do string theory and quantum gravity. And you have debates about whether solutions are solutions and this kind of thing. And those debates are important and healthy. And at the same time, you'd like to be able to maybe avoid some of that and just use the formalism of OPEs, conformal weights, things that are defined rigorously on the CFT side. And in the same way that's been done for ADS amplitudes by using CFT correlators, somehow come to bear on whether this type of vacuum is possible when you take a large C limit of some sequence of fields. What this means in terms of the operatorial content of the theory is that there's a certain type of gap in the spectrum. This isn't the higher spin gap. Here we imagine we're always talking about large C, large higher spin gap theories, but the question is whether you must have some tower of operators whose dimensions are order 1, or whether you can somehow not have this and still have a consistent CFT. So here's your vacuum state, your identity operator, and say here is your gap scale, maybe up here somewhere. Charge. You can have some operators here in a scale-separated solution, and it would be scale-separated solution. You can have some things here, but just not too many. If you had a KK tower, you'd have some infinite sequence, which grows parametrically as you take delta much greater than 1, but much less than delta gap. The statement of scale separation is not the statement of the spectral gap for the lightest operator. It's more refined. It's a statement about whether, as you take sort of delta in this intermediate region, much greater than 1, but much less than delta gap, say, you are allowed to have some number of operators which, doesn't scale at all with delta. Just, in other words, a finite number of light operators with respect to both C and delta gap. These would be like some fixed moduli in some bulk solution. So are you allowed to have something which is very sparse at low energies in your CFT operator spectrum? That would imply that in the bulk, this extra compact space, say in the string context, is sufficiently small that all the excitations are gapped up to the higher spin gap scale for some power of it. So we don't know the answer to this question. I think about this question. I think answers will come, but they're not out there yet. And there are certain portions of this question which you can answer. And in ADS3, it's also a live question. But people don't often talk about it in this language. What you hear instead is that people try to construct theories of pure gravity in ADS3. But that's just an extreme version of this, where you have nothing here, or even here, up until the Planck scale. But I think it's useful to think of these as two versions of the same problem. And so next time, when we move down to ADS3 CFT2 for the last lecture, we will talk quite a bit about this suggestion that maybe there's a theory of pure gravity in ADS3, which would be dual to a 2D CFT with a very large gap to even the first light Virasoro primary operator. But in higher dimensions, the scale separation question is sort of a version of that, which is interesting. And so let's stop here.
This G K greater than 3 not allowed. Is there anything that you can say about the properties of that infinite tower? Or just like some space? Or is it just that there is a different tower? It's something that has to come in.
I think there's nothing, apart from some specific bounds on low K, there's no kind of asymptotic statement. that have come from these S-matrix bootstrap papers. Yeah. But there should be some kinds of constraints on those relative coefficients. Yeah, I wonder if there's some kind of asymptotic scale that would be necessary for resummation back down below the planar shape. But there are no results along these lines in these newer papers. There might be something. Around. Yeah, I'm not sure. Not sure.
So again, yeah, so this large spin story, it was made rigorous, right? So at first it was also sort of like asymptotic for large J, and then it was made rigorous. So have people tried doing that for just large C, try to see if it can be extended in general CFTs?
For large C?
Yeah, so the same story, like how it was made done for large spin. Now it's also true for finite spin.
Yeah, the problem is that you're changing the theory itself as you change C. So this is a question about theory space.
Yeah.
So I don't see any immediate applicability of those types of methods to this question. But still, you could try to understand the asymptotics of the 1 over C expansion and say something about the form of the resummations or the analytic properties of this, or when one needs research. So, but yeah, I think that the properties of 1 over C expansions in CFTs are not super well understood. In general, they're expected to be asymptotic. There are many examples where these can be developed to all orders, resummed, but a general statement about the relation between finite C and large C CFT data is kind of lacking. And in general, if we think of CFTs as isolated points generically, then we need to work a bit to even define what this means. And the expectation would be, yeah. At first, the expectation for the result, for the answer is quite unclear, because like why you would expect something which is some continuous function of C which has support at the points where there are theories but can actually be defined in between some analytic way. I mean, this is like a totally wild idea which could be true, but just as opposed to the idea in the large spin story where now we know there are some light ray operators that can be defined which interpolate. I mean, in theory space, who knows what the ray structure is. So, yeah, very interesting question. I just don't think those methods would be applicable to it without more foundations.
One question. Okay, if not, let's think again.